Hello and welcome back. In the previous video, we talked about atomic vectors, which are vectors where all of the elements have to be the same type. And we talked about different types that you can put in atomic vectors. In this video, we're going to talk about lists, which are non-atomic vectors. That means that each list element, each element of the list vector, can be basically anything. So we'll see lots of examples of how that works. Okay, so let's go into our first example. In the previous video, we worked with a matrix. Recall that a matrix is a vector, but it has a dim attribute. So we're going to define a matrix, same one we were working with before. The numbers 1 through 8, 4 rows, 2 columns. On top of that, we are going to define column names and row names. So col names. By the way, when I type here COLN, in RStudio, it gives me a little shortcut. So what I can do is I can hit Tab. That will complete col names. If I do this, that calls that. We won't use that right now. So I'm just going to do col names, and it will open up the parentheses. So I'm going to use this as a replacement function, and I'm going to name the two columns column 1 and column 2. And I'm also going to name the rows R1, R2, R3, and R4. And then we'll print that out. So just a reminder, I'm putting my cursor here, and I'm going to do Control-Enter to send it over to the console. That runs the line. Control-Enter, Control-Enter, Control-Enter. And so this prints out the matrix that we just defined. It's a 4x2 matrix containing the numbers 1 through 8, and it has column names and row names. Now, we looked at the functions col names and row names. It can be used both as a replacement function and a function that returns something. So here, if I call names m, it returns the 2 column names. If I call row names m, it returns the 4 row names. There's also a function called dim names, which returns both the row names and the column names. And if you think about what kind of thing it would have to return, it could give you a big long vector of 6 things, so column 1, column 2, row 1, row 2, row 3, row 4. But that wouldn't allow you to say, oh, these ones are the column names and these ones are the row names. So what it actually returns looks something like this. So dim names m has this double square bracket thing 1, and then below that it looks like a regular old atomic vector. In this case, it's a vector of character strings. And then there's a number 2 here in double square brackets, and that is also another atomic vector. This time it's length 2, but it's also a character vector. What we're looking at here is a list. So it's a list with 2 elements, 1 and 2. The first element is the atomic vector here, and the second list element is this atomic vector. So this is a good use case for a list where you want to be able to return both the row names and the column names. You can't really put them in a matrix because this one is longer than this one. And so the only option here is to put it in this kind of unstructured type of data object called a list. Now to create atomic vectors, we use the C function. For concatenate. The analog to that for list is just called list. So let's make a list here. List, and it works exactly the same way as C, where you put the different list elements in order, separated by commas. But now these list elements can basically be anything. So 1 for letters 1 to 10, and let's do something weird. We haven't talked about functions yet, but I'm going to define a function, and I'm going to put it in a special value too, null. So let's run that and look at the output. we get this over here. So this is a list with 4 elements. The first is that vector, the second is that vector. The third is this function. So this is the first time we've seen the definition of a function. And this is a null value. So you can see this operates a little bit differently than how the C function works. One thing is that if you put null in C, it just basically ignores it. Another thing is you can't put a function in. Another thing is it didn't do automatic coercion. So it didn't coerce this letter vector of character strings to match the type of this integer vector. Actually, in C it would, well, actually, let's do this real quick. So just a bit of review. Let's define A instead like this. I'm going to define it here. As we've just seen, I'll put the null here. As we've just seen, letters 1 through 10. Letters is an object in R. You can just type it in. It's an object in R that has the 26 lowercase letters, A through Z. This is the first time we've seen subsetting. So letters itself is an atomic vector. We use square brackets to subset atomic vectors. We haven't gotten into that yet. That's because we're going to do an entire module on subsetting. That's coming after this video. But this is how you would extract the letters. So if I run this, it does this coercion 1, 2, 3, 4 as character strings. You can tell that because there are quotes there, and then appends this to the end. The list function works differently. It doesn't try to put them together. It just keeps them as separate list elements. Okay, so let's run this, and let's look at type of. This is a list, and let's look at class. This is also a list. Now, type of, as we defined it before, doesn't really make a lot of sense because the different elements of the list could have different types. But in R, it just returns list. The more interesting one is class that returns list. Now, just like atomic vectors, lists can have names. So each element of the list can have a name. So let's look at an example. So instead of just defining 1 to 4, I'm going to give it a name, my numbers, some letters. We'll define a function. Let's do log x. Okay. We'll run this in a second, but let's look at what happened here. When I made this line really long, it saved space. It didn't wrap around automatically. It just let me keep going. But this is a bit of a problem because if I'm glancing at the script, I can't really see the whole thing all at once. So in R, R doesn't care about white space or enters. So what I would usually do when I'm writing this code is I would put this on a new line, and this on a new line, and this on a new line. So now it takes up a lot more space, but at least I can see everything all at once. So this is much easier to digest. So this is another example where the two sets of code, the one that was a really long line that went off the page, and this do exactly the same thing. However, I would say this one's better because it's a lot easier to read. So pay attention to these kind of things when you're writing R code, because this can really make a difference if you come back to the code later, or you want to show it to someone else, or you want to debug your own code. It can be hard to decipher it when things are running off the page. Okay, so that's a bit of a digression on style. So let's run this, and let's look at A. Now, instead of this square bracket, the double square brackets, you have $, my numbers, $, some letters, and $, fun. And just to preview a bit, if I wanted to extract the first element, I would use double square bracket 1. That will give me those letters. Or I can do, just like it's written here, my numbers. Here again, it's giving you a preview. When I start typing here, RStudio is saying, oh, you probably want my numbers. So I can just hit tab and it'll complete it and it'll run that. So this is just a preview of the next lecture on subsetting. This is how you would grab that element. So now we can see that they have names. So if I do names of A, I get that. Think about this for a second. What type of object is A? What type of object is returned by names of A? Well, this looks like a length 3 atomic vector whose type is character string. So I could do type of names A. It's a character. Okay. Let's see, I put this in the wrong spot. Okay, another cool thing about list is, like I said, each element of the list could be basically any R object, and that includes other lists. So lists can have this nested structure. So let's look at an example here. So let's say B, we already have a list laying around called A, and I'm going to give it another vector, just a set of random normals, just to put something in there. So if we were working with atomic vectors and we had an atomic vector A and we concatenated it using C instead of list with another atomic vector, what it would do is it would just return another atomic vector where they were put together. List is not going to basically make another list element of A with rnorm 10 attached to the end. It's actually going to create a list whose first element is the list A and whose second element is this vector. So let's just look at that. Okay, so here, this is indicating this is the first element of the list B. This is the first element of the list B, this whole thing. So it itself is a list whose first element is my numbers, whose second element is some letters, and whose third element is fun. This notation here is saying, here we're looking at the first list element of B, whose name is my numbers. This is the first list element of B, who has a list element called some letters. This is the first list element of B, who has a list element called fun. Now down here, this is the second list element of B, which is an atomic vector, double precision of length 10. Okay, so important point, it doesn't just append rnorm 10 as another list element of A. This is actually going to give you a list of length 2, whose first element is a list. And we can verify that length of B is 2, and B1 is that list element, and length of B1 should be 3. Okay. So just to reiterate, the list function works a little bit different from concatenate, but in the sense that you can nest things, where concatenate would just put them together. Now, if you've done any R programming, you've probably run across data frames. And most people think of data frames as a special type of matrix. But I think it's useful to go back and forth between thinking of a data frame as a matrix and also as a special type of list. So let's see how that works. I'm going to create 3 atomic vectors. First one is a character vector. The second is, this will be a double precision because I'm not putting the L's in there. And the third one is 1 plus 0i. This is a complex. By the way, I'm not picking very informative variable names. You should pick informative variable names when you're writing real R code. I'm just naming like A, B, D. Now, why did I skip C? Why didn't I do this? The reason is this would work, but this is a bit confusing because we have a function called C, and then we have an object also called C. So try to avoid naming your R objects the same name as functions. It will still work, however, it could be a bit confusing. Okay, so let's run these, and we'll print them out. I'm just going to do that in the console. There's A, B, and C. Sorry. Good. That's the function C. A, B, and D, that's that complex vector. Okay, so importantly, so these are all atomic vectors, and importantly, I made them all the same length. They all have length 3. Now, if that's the case, I can put them all together in a single object. One way of doing them is to put them in a list. So let's try that first. I'm going to call that LL, for lack of a better term. So when I do this, it's not going to do coercion to make them all the same type. It's going to put them in a list. Oh, I put in C. See, that's why you do that. All right, so if I do that, it doesn't try to coerce them. List won't coerce on purpose. It's just a list of 3 atomic vectors, all of length 3. Now what a data frame does is it does something very similar, but it notes that they're all the same length, and so I can kind of organize them in a matrix style object. So let's just try that. The function is called data.frame, and it works similarly to both C and list. I just separate the objects by commas. And if I run this, now it organizes things in a matrix-like object in the sense that there's a number of rows and there are a number of columns, and it puts them in this rectangular format. However, if I had tried to put these together in a matrix, since a matrix is a special type of atomic vector, the elements would have to be all coerced to the same type. And if you look, the highest type would have been character string, and so they would have all been converted to a character. However, these are not characters. So if I do dat, if I grab the one called B, and I do type of, this is still a double. So it doesn't do automatic coercion. So a data frame is a special type of object that behaves similarly to a matrix, but it allows each column to have a different type. Okay, so you can do similar, since it works kind of like a matrix, you can do similar things. So you can set and get the column names. So here the column names are A, B, and D. These were just inherited by whatever the variable names were that we put in there. You can get row names. By default, it just numbered them 1 through 3. And importantly, the row names are characters. These are not numerics. Now, so these are situations where it's treating this object, a data frame, like a matrix. It has column names and row names. It's organized in rectangular format. However, there's other attributes of a data frame that will treat it more like a list. So let's see, we had a matrix up here somewhere. Yeah, M. So we have a matrix M. If I do class M, it's a matrix. If I do length M, Now think about what this will do. So matrices in math don't really have lengths, but I told you that in R, a matrix is just an atomic vector with a dim attribute. So if I do length m, it's going to think of this as an atomic vector, and it's going to say 8. Now if I do the same thing to this data frame that we just created, so if I do length dat, it gives me 3 instead of 9. Recall, this is dat here. It has 9 total elements. So this is treating dat as a list. So it's treating dat as a list with 3 elements, which are the 3 columns, which are atomic vectors of the same length. Okay. There's other functions that also treat it as a list. Names won't give you both the row names and the column names. It just gives you the column names. So it's treating it as a list whose 3 list elements are the 3 columns. If you do, let's see, type of, I actually don't remember what this gives. It says list. If you do class, it should say data frame. So in this sense, it's kind of different from a list because class doesn't return list, it returns data frame. But in this sense, it is. Now, there are other attributes you can get. You can get the number of rows. This works the same as a matrix. Number of columns. This works the same as a matrix would work. We could apply this same thing to M. And we can also, I believe, we can get dim names. Yes, and this returns a list. Okay, a couple other features. You can also assign names. So here we didn't give these columns informative names, and it just inherited these variable names. But we could say words. The first one is called words, the second one's called reals, and the third one's called comps for complex. So here it gives informative column names. You can also convert a matrix to a data frame. There's a function called as.dataframe. So we have M sitting around. M is a matrix. Now it looks a lot like a data frame, so there's really no difference here, but you can spot the difference. Well, you can know that this is not a matrix because the columns have different types. Here you can't know that this is a matrix because this very well could be a data frame and the way it's printed out. The way you would check for sure is to say class. So that tells you it's a matrix. Now you can convert a data frame, or sorry, a matrix to a data frame with as.dataframe. Now you can see, like I said, the printout is exactly the same. But if I were to do class as.dataframe M, this is now a data frame. When you do that, the column names will get transferred. So so M is that, M, okay, think about this. Is M now, I ran this line of code. Is M now a data frame? And the answer is no. And the reason is doing this returns something, but it didn't assign it to anything. If I really want to change M to be a data frame, I have to reassign it like this. Again, it's not going to look any different. However, now it's a data frame. Okay. Now, if I were to change the column names, I could do it this way. So this works both on a matrix and a data frame. Now there's another implementation of the concept of a data frame in R, and these are called tibbles. So to access tibble, you have to load the tibble library. This is the first instance where we're loading an external R library. That's because data frame is in the base R library, which gets loaded automatically. But there's lots of other libraries out there that people have written for R to give extra functionality. One of them is called tibble, which gives the tibble. So if you run this, you may get an error. If you get an error, it should say something like library tibble not available. You'll do install.packages tibble. So it will install tibble and any other packages that tibble depends on. Okay, so I've loaded the tibble library, and you can use it. One way to use it is to just convert an existing data frame to be a tibble. So we have a data frame called dat, and I'm going to convert dat to, actually no, I'm going to give dat, so this is important to get this right. I was about to say I'm going to, with this line, convert dat to be a tibble, but that's not what this does. This actually doesn't convert dat at all. This would return the data in dat as a tibble, but it doesn't actually change dat. If I want to get the tibble in another object, I have to do an assignment. So that's tib. And you can see it has a little bit of extra functionality. For example, it prints out what it is. It's a 3x3 tibble, which is like a data frame. It gives the column names, and it tells you the types of each column name, which is kind of useful. You can also use the tibble function to define them. So you would say tibble. So this just works just like data frame, data.frame function. So this is a way of doing the same thing. One of the nice things is about tibbles, and we're not going to get too deep into this right now, is that it gives you a nicer printout. So let me show you an example of that. So I'm going to make a really big data frame. And the way I'm going to do it is I'm going to make a really big matrix and then convert it to a data frame. So it's going to have 4,000 elements, 200 rows, and 20 columns. Now if I create that, then this is a big, big data frame, and print it out. It prints out this kind of mess of stuff, which is useful sometime if you want to look through, inspect every element of a big data frame. But actually at the end, R complains. It says, I don't want to print that much out because I've reached the max.print value, and it's omitting 150 rows. So this is a bunch of stuff on the screen that may be too much to handle. If you instead make this a tibble, and try to print it out, it doesn't try to print out the whole thing. And also it does some nice coloration. So it makes all the negatives red and the positives black. And then it gives you some more information about what else is not printed. If you want to have some control over what gets printed, you can do print tib width equals 100. Let's see. That tells you how many places to print out. It's only printing 18 of the columns though. So two more variables, v19, v20. Okay, so there are other implementations of data frame. This is part of the tidyverse, if you've heard that, and we'll get into that later in the course. Okay, the very last thing I want to tell you about is I said above that the columns of a data frame all need to be atomic vectors of the same length. That's not quite true. What really needs to happen is they all need to be vectors of the same length. And you can see how this works. We can make a data frame that has things that we expect. So I'm going to just put some nearby cities. So this is a character vector, atomic character vector of length 3. And I'm going to give their coordinates. Excuse me while I type this in. And then I'll explain what this is. Okay, now I should put this on its own line, so let's see. All right, so let's try to parse this. I'm not going to go through trying to format this at this point. So we're calling list. So the second element is going to be the coordinates in latitude and longitude. We're calling list, and we're giving it 3 things, 3 atomic vectors of length 2. And putting that in list. So if I were to just run this, you can guess what this will look like. Looks like that. And I have to make this work, I have to wrap it in the I function. We could talk about that later. And then I can run this. So this is going to be a data frame whose first column is an atomic vector and whose second column is not an atomic vector, it's actually a list, but its length is the same as the first column. So we run this, no errors. So this actually works. And we could grab the coordinates like this. So this might be useful to you at some point. This idea is used by the SF package, which is for spatial objects, to keep the coordinates in a single column as opposed to having separate columns for like latitude and longitude. Okay, so it's not quite true that each element of a data frame has to be an atomic vector of the same type. They just have to be a vector, and they all have to be the same length. Okay, that's it for lists and for this video. In the next one, we're going to talk about subsetting. We haven't really gone into subsetting vectors and matrices and data frames. There's lots of different ways to do it. So we're going to get into that in great detail in the next lecture. See you later.